Well, thank you for inviting me to come out and visit. I'll be here again for the conference in August, where I'll be speaking about this topic much more generally. So today I'll be able to dive into a lot more detail with you. So I'd like to acknowledge all the people who are working hard on this stuff alongside with me, especially Francisco Mueller-Sanchez, who will be joining me at Colorado as a postdoc in the fall. And also a couple of students, James Diekman and Kyle Schlunz, who've been working on projects in this field. So I'll start with a very oversimplified view of galaxy mergers and their role in galaxy evolution. So if we start with a galaxy, merge it with another galaxy, this triggers inflows of gas towards the center of the merger that can light up bursts of star formation and fuel the central black holes as AGN. So this leads to this very chaotic Euler state here. So the black holes continue to grow in mass rapidly until they fuel some kind of feedback that can blow out the remaining gas and dust in the merger remnant system, which puts a halt to any further star formation, starves the black hole, so the AGN begins to dim, the whole galaxy fades and reddens until you're left with a remnant that looks like a red and dead elliptical galaxy. So this sort of view of galaxy mergers leads to several open questions in the field of galaxy evolution. So we've seen that galaxy mergers can trigger AGN activity, but AGN activity can also be triggered through stochastic means. So we don't really understand what the relative roles of these two methods are. When are AGN induced by mergers? When are they through stochastic accretion of gas? We also don't know how much black holes grow in mass during the course of a merger. We see them accreting mass, but how much of that mass growth occurs inside of mergers versus outside of. And finally, a merger between two galaxies leads to the merger of two supermassive black holes, which is, of course, interesting in the context of gravitational waves. So in the course of this talk, I'm going to introduce dual supermassive black holes as a new and unique observational tool for getting at these sorts of open questions in the field of galaxy evolution. So here's another picture of a galaxy merger in progress. And here I've put red dots at the center of the galaxies to denote the supermassive black holes at the centers. So we can follow along with what happens to the black hole pairs as the merger progresses. And we can watch as they're brought closer and closer together until they're brought into the same merger remnant galaxy. And at this phase is known as the dual phase. The two black holes have separations of order a kiloparsec. They're moving in the galaxy velocities relative to one another of a few hundred kilometers a second. So we have dynamical friction from all the surrounding stars is dragging these black hole pairs closer together until they form a gravitationally bound binary system. So here the separations are much, much smaller. We're talking less than a parsec, and the velocities are also much larger at this few thousand kilometers a second of these black holes orbiting around each other. Now the details of this next step could be a topic for a whole nother day, but we expect that these binary systems should ultimately coalesce, emit gravitational waves, and leave us back to the paradigm of a single galaxy with a single central supermassive black hole.
Can I ask you,
yes.
What is your definition of dual?
Yes. So for the purposes of this talk, it'll be black holes with separations less than 10 kiloparsecs. And I do want to...
More than.
But more than, well, the smallest separation that's been found is 7 parsecs. Yeah, anything that's not gravitationally bound yet. So this brings up an important distinction between these two states, which is the dual phase. You've got one galaxy with two black holes, but they're far enough apart that they don't necessarily know about each other. Their dynamics are dominated by the potential of the host galaxy, so they're orbiting around in that. Whereas in the binary phase, they're so close together that they're gravitationally bound to one another. So that's the major distinction between this phase and this phase. But I do want to talk about the binary phase a little bit. In the course of this program, you probably already have or will hear a lot more about binaries from some of the people in this room. But I just want to mention one thing about binaries. So there are several different observational signatures of binaries that one can go out and look for. One of the first ones that was proposed was to look for double-peaked broad lines in galaxy spectra. So the idea is you have these two black holes they're orbiting around, you can see their broad lines have shifted velocities relative to one another by a few thousand kilometers a second. So this could be a signature of a binary system. But it turns out that these double-peaked broad lines can also be produced by disk emitters. So basically you're seeing one black hole and rotating accretion disk, so you're seeing the blue shift and red shift because of that rotating accretion disk. So because of difficulties like this, it's hard to get something from a spectra alone that gives you confirmation of binary black holes. What you would really like to see is spatial resolution of the two black holes. But with these sorts of separations, these are much less than a parsec in other galaxies. That's going to be really difficult to do observationally. So there are many, many candidates for binaries that have been found with a range of different observational techniques. But so far, there have been no spatial resolution and confirmation of the two separate binaries. So I focus on the dual phase instead of the binary phase because this represents the smallest separation black hole pairs that we have been able to spatially resolve and confirm so far. So the way we can find dual supermassive black holes is if they're both powering AGN as dual AGN. And if you do simulations of galaxy mergers, you can follow along with the black holes and the mergers and when they turn on and off as AGN. And Sandor van Vossenhove has done this. This is a plot from his paper showing the velocity separation between the two black holes in a merger plotted against the separation of the black holes. And this color bar shows the amount of time that the two black holes spend active as dual AGN. So you can see in this example, when the black holes reach separations less than about 10 kiloparsec, which is the dual phase, they can spend tens or 100 mega years at a time active as dual AGN. So there should be dual AGN out there, but surprisingly few dual AGN have been found. So this was the state of the field in 2008. There were exactly 4 known dual AGN systems. And perhaps the most famous one is NGC 6240. This is a nearby Euler galaxy. And the Chandra image of the center of the galaxy here shows these 2 blue peaks here that correspond to 2 AGN separated by about a kiloparsec. So all of these systems were discovered by chance. They're all at very low redshifts, 0.02, 0.06, 0.05. And they were all confirmed as dual AGN through detection of the 2 AGN sources either in X-rays or in radio. Okay. So if we want to eventually use dual AGN for studies of galaxy evolution, we'd like to build up a bigger population. And then you can start to get at these sorts of questions that I introduced at the beginning of the talk. So for example, since dual AGN are AGN in the middle of a galaxy merger, we can use them to study how often AGN are triggered by galaxy mergers as opposed to stochastic accretion of gas. And for example, there's been a suggestion that the fraction of AGN in mergers has a dependence on the AGN luminosity, so that the more luminous AGN are preferentially triggered by mergers. So this is the type of thing that we can study with a sample of dual AGN. Dual AGN are also actively accreting black holes in the midst of a galaxy merger, so we can use them to measure how much black hole mass growth occurs during mergers. So the tightness of the m-sigma relation can be understood in part if black holes build up some amount of their mass in the course of a galaxy merger. So we can use dual AGN to measure what the mass accretion rate is of the black holes at different phases in mergers. And finally, since dual AGN are the smallest separation black hole pairs that we've been able to observationally resolve and confirm so far, they can offer some of the tightest observational constraints on the black hole merger rate, which is necessary for future gravitational wave experiments for them to know how often supermassive black holes should be merging and what their masses are. So what we'd like to do is move past these chance discoveries of dual AGN and get at a way of building up a large catalog of them to use for these studies of galaxy evolution. So what we need to do is a systematic approach to this problem. And so I'll be presenting one systematic approach to building up a sample of dual AGN that relies on large spectroscopic surveys of galaxies. So the benefit to approaching this problem systematically also is that we can push this out to larger redshifts. So all of these chance discoveries are at very low redshifts. But if we do this systematically, we can start to look at how these different properties evolve as a function of redshift. So I'll boil down this technique into 3 steps. We start out with spectroscopic surveys of galaxies where we look for AGN that have double-peaked emission lines. So this is somewhat of an analogy to the double-peaked broad lines that I mentioned as a possible signature for the binary supermassive black holes. But here the separations between the black holes is large enough that the narrow line regions are not overlapping. So we can look at double peaks in the narrow line regions instead of the broad line regions. Now, for the binary double peaks, the issue was that those double peaks can be produced also by disk emitters, and so you don't always know what you're looking at. We have the same sort of issues with double peak narrow lines. They can be produced not only by 2 AGN, but also by a single AGN with an outflow, where you're seeing the redshifted and blue shifted components of the outflow producing the double peaks. Or you can also get it from the same sort of rotating disk or narrow line gas kinematics, or a combination of effects. So this is the reason why this is not a one-step approach. We can't just find double peak things and stop. We have to work on weeding out what is actually producing the double peak. So because I was at Berkeley at the time I started doing this, I started out by applying this method to the Deep 2 Galaxy Redshift Survey. And in it I found 2 examples of double-peaked AGN. So these are the oxygen 3 lines at 4959 and 5007, and you can see the double peaks in each. So these are at relatively high redshifts, 0.6 and 0.7. So whereas the dual AGN that were known at this point were all at redshifts less than 0.06. So this is starting to push this out to higher redshifts if these are indeed dual AGN. And then later since all this data was taken with the DEMOS spectrograph on Keck, this is Longslit. So we have 2D spectra for these objects too. And here's cutouts of what they look like. So this is only showing the 5007 emission. This is a wavelength spatial position along the slit. So where we had these double peaks here, we see the 2 emission components. But because we have the spatial axis, we can measure the spatial separation of the 2 emission components along the slit. So here, the separation is 1 kiloparsec. Here, it's 2 kiloparsecs. So if these are dual AGN, you start to get a picture of what's going on. We have 2 AGN separated by 1 or 2 kiloparsecs, moving relative to each other by 400 or 600 kilometers a second. So we also took this double peak technique and applied it to the AGES survey. And there we also found 2 double-peaked AGN. These are at more moderate redshifts. The median redshift for AGES was 0.25. And we're finding, 1% of the type 2 AGN are double-peaked. With deep, it was 2%, so roughly the same. So if we're looking for spectroscopic signatures that are extremely rare, so only 1 or 2% of AGN are showing these double peaks, then to build up a large sample, we really want a really big spectroscopic survey to go through and do this with. So what you need is Sloan. And so there have been a series of several papers that have gone through Sloan looking for double-peaked AGN, and they found 340 of them. And these are at very low redshifts. The median redshift is 0.1. But again, it's only 1%, but because you're working with so many AGN, you can still find a large number. So for the rest of the talk, I'll be focusing on this large sample of double-peaked AGN in Sloan and trying to weed out which of these are actual dual AGN. So the benefit of Sloan is that it's huge. The drawback is that it uses a fiber-fed spectrograph. So whereas with Deep 2, we had all these nice long-slit spectra that gave us 2D spectra where we could see the spatial extent of the emission, we don't have that with Sloan. Everything is just combined into this 3 arcsecond fiber. So we don't know the spatial extent of the emission in the galaxy to help us weed out what's going on that's producing the double peaks. So what we do is we obtain follow-up long-slit spectroscopy of the double-peaked AGN in Sloan to get a picture of what's going on. So the reason we do this is because of things like outflows. So this is a nearby galaxy with a well-known outflow. This is a map of the oxygen 3 emission from the outflow. So all this emission has various red shifts and blue shifts relative to systemic. And if you add it all up, you get this double-peaked profile, which by now should look familiar to you, except this time it's not being produced by 2 AGN, it's being produced by 1 AGN with an outflow. Now if we look at the 2D spectrum of this outflow, spatial position along the slit, this is the wavelength or velocity axis, we can see this very extended emission. It's extended both in velocity and spatially along the slit. And so this sort of emission can be modeled by this biconical outflow feature. So whereas outflows and dual AGN can both have these double-peaked profiles that are hard to tell apart, their 2D spectra can look very different. So for the outflow, it's very extended. For the dual AGN, it can be very compact. So you have 2 emission components associated with the double peaks that are just tight instead of spread out like the outflow. So by doing follow-up Longslit spectroscopy of the Sloan sample, we can get this sort of information to help us figure out what's producing the double peaks. So we've done this for 132 of the 340 double-peaked AGN in Sloan. And this is a good quiz slide if you're an observer to see if you can name what all these telescopes are. So we've got, everyone knows Keck. This is Lick, this is Palomar, this is the MMT, Gemini North, and Gemini South. So basically we use the bigger telescopes for the higher redshift objects and the smaller telescopes for the lower redshift objects. And what we did was, well, here's an example of one of the double-peaked AGN. Here's what it looks like, the host galaxy. Now, if there's 2 AGN in there or an outflow, we don't know what the orientation is. We don't know where the AGN should be. So since we're doing long slit, we need to observe this at 2 orthogonal slit position angles so we can be sure we don't miss where the action is. So what we do is we lay down the first slit along the long axis of the host galaxy, and that gives us a 2D spectrum that looks like this. So here are the 2 emission components corresponding to the double peaks. We can measure the spatial separation along the slit, call that x1. Let's observe again at the orthogonal position angle. That gives us this spectrum. So we've still got the 2 emission components. This time they have a much smaller spatial separation along the slit, call it x2. So we've observed this galaxy at 2 orthogonal position angles, measured 2 separations between the emission. So we can combine all this to give us the full separation on the sky of the 2 emission components. So we've done this for the sample of double-peaked AGN in Sloan, and this is the result. This is a histogram of the spatial separations of the 2 emission components on the sky for the double-peaked AGN. So a 3 arcsecond Sloan fiber at this redshift range could lead to physical separations up to 15 kiloparsecs. So it's striking that we don't see any separations that are larger than 5.5 kiloparsecs. So what that means is whatever's producing the double peaks is not a large 10 kiloparsec scale effect. Now, the smallest separation we measure is 200 kiloparsecs, 200 parsecs. So we don't have any cases where we don't resolve the difference in position between the 2 emission components. So that means there's not a very small scale effect, sub 100 parsec scale effect that's producing the double peaks. Instead, the median separation is around a kiloparsec. So whatever is producing the double-peaked AGN is a kiloparsec scale effect, either dual AGN or outflows. Okay, so this follow-up long-slit spectroscopy is already giving us some information about what's producing the double peaks.
The gas that is producing the emission, how far is it from the AGN?
Well, the narrow-line region, so it's about 100 parsecs.
So is that something? I mean, is that how we should interpret the lack of small separation? Rotation, the first X over there, the rotation of gas in this less than 100 parsecs. Without with small.
Yeah.
Do we start losing them when the separation between the AGN becomes smaller than the size of the narrow-line region?
Right. And the other thing to worry about is you could have dust in all sorts of different configurations, so maybe you're not seeing the entire narrow-line region. But yeah, so you're not seeing anything less than that scale producing the double peak. So it may be that things like this just don't even produce the double peak signature. So that's why we're not seeing them. Right. Right. So another.
How is it that many, or some at least of the previous set of double emission line objects proved to be outflows, but none of your 130 are?
Oh, some of them are.
Oh, okay. Okay, so we're coming
yeah.
to this. All right.
So I've got dual AGN and outflows as the open possibilities here, and I'll show you how the profiles of the 2D spectra can help sort this out for us. So. Yeah. Oh, I'll be showing that plot. Yes. Okay. So another thing we noticed was that in 60% of the cases, the double-peaked AGN correspond to these spatially compact emission components, so they're compact spatially and in velocity, whereas the other 40% are extended in a wide variety of different ways. They kind of have these messy profiles. So these extended profiles remind you of what the 2D spectra look like for these outflows, right? So here's the outflow I was showing earlier. It's got this extended emission. It kind of looks like some of these. Here's another example. This is actually one of the double-peaked AGN in Sloan, where radio observations showed that these double peaks are actually being produced by an outflow. There's only one AGN here. And here's what the 2D spectrum of it looks like. So there's that extended emission again. So it may be that more of these spatially extended objects turn out to be outflows. So that's something that we have to wait till step 3 to confirm. But this is one of the things that we're looking at testing, is whether from the 2D spectra alone we can get an idea of which ones are outflows here. Spatial distribution? No. They have the same spatial distribution as the compact. So I don't think it's going to be as simple as all of these are outflows, all the compact ones are dual AGN. I don't. But I would guess that probably more of these turn out to be outflows, and probably not as good a place to look for dual AGN. But we need confirmation of what system is what to know that for sure. So this is just sort of some tantalizing evidence of something we could use down the road. Now there have been several groups that have been doing follow-up adaptive optics imaging of the host galaxies of the double-peaked AGN. And they're finding in some of the cases you can see 2 stellar cores in the host galaxy. And in some of these, we're finding that the 2 emission components we see in the long-slit spectra spatially coincide with the location of the 2 cores. So here's a galaxy with a double-peaked profile, 2 stellar cores, each with AGN emission coming from the center. Okay, so this is a very strong candidate for a dual AGN. And when I've talked about this with people before, I've said that I would bet my car that these will turn out to be dual AGN, but I drive a 13-year-old Camry with 140,000 miles on it, so that maybe doesn't hold a lot of weight. But I just bought a house, so now I can say I bet my house. Maybe no. Mike's tisking me. Yeah, the bank might not want me to yet, but I would bet that these probably turn out to be dual AGN. But I also want to caution at this point that this is a very young field. There's still a lot we don't know. So at this point, I think it's very important that we get absolute direct confirmation of dual AGN. And it may be that after we get enough confirmations, we'll understand what's going on enough that this will be sufficient and we won't need to go get confirmation every time. So, but for now, this leads me to the final step, which is to get direct observational confirmation of dual AGN through detection of the 2 AGN sources, either in X-ray or in radio. So in X-ray, the idea is to see these 2 AGN sources, like in NGC 6240. In radio, the idea is to measure the 2 flat spectrum radio cores as direct confirmation of 2 AGN. So in the X-ray, we've gotten Chandra observations of 13 of the double-peaked AGN in Sloan to do this. And in radio, we've got 86 double-peaked AGN that will be coming down the hatch with Jansky VLA. So for Chandra, the idea is to do something like this. Here's our Sloan double peaks. Here's the follow-up spectrum from Lick, where we see these two emission components. And then the Chandra observations show two X-ray sources that coincide exactly with where the two emission components were in the long-slit spectrum. So this is exactly the sort of thing we're looking for as confirmation of dual AGN. And this also nicely illustrates all three steps in the process, right? Double peaks, follow-up long-slit, confirmation with Chandra. Now on the radio, I'd like to advertise the work being done by Francisco Mueller-Sanchez. Francisco is a postdoc at UCLA right now, working with Matt Melkin, and he's going to be joining me as a postdoc at Colorado starting in September. But he's already gotten his hands dirty starting to work with the VLA data that we have coming in on these double-peaked objects. And so here's one of the first images that he made, and you can see the two radio sources. So this is an example of two AGN that we found in the radio. So we hope to find many more that look like this. The energy in radio? I don't think he's gotten that far yet. Oh, I'm sorry. Oh, 8 gigahertz. Yeah. Yeah, this is from the VLA data workshop. So this is sort of first preliminary results in learning how to do this. But I think it looks fabulous. Okay, so I've sort of summarized a systematic way we can go through large spectroscopic surveys of galaxies and whittle down which ones have dual AGN. Now I'd like to take a moment to talk about dual AGN in the context of galaxy mergers. So models have shown that the occurrence rate of dual AGN is consistent with the AGN activity being triggered by galaxy mergers. And in observations, we see evidence for merger-triggered AGN, dual AGN as well. So this is work done by Mike Koss using the Swift BAT AGN sample. So he started with a sample of 187 ultra-hard X-ray selected AGN. And what he did is he looked for whether the AGN had companion galaxies near them. And he measured the separation between the AGN and the companion. And then he went and looked at, well, how many of these companions are also AGN? So what he found was for the companions that were the furthest away, so you have an AGN with a companion galaxy 60 to 100 kiloparsecs away, only 10% of the time does that companion also have an AGN. But as you move to smaller separations, so here you have an AGN with a companion 1 to 15 kiloparsecs away, half of the time that companion is also an active galaxy. So there's evidence here for the AGN pair fraction increasing with decreasing separation, which suggests that maybe galaxy mergers have something to do with the triggering of the AGN activity. So since we think some of these double-peaked AGN are dual AGN, we wonder whether they're also associated with galaxy mergers. So I found that on average, double-peaked AGN are about 3 times more likely to have a companion galaxy than just the general AGN population. So here are some examples from the AGES survey. So in the crosshairs is the galaxy that has double-peaked lines. So this one has double-peaked lines, this one has double-peaked lines, and then there's that companion right there. So this one, we do have a spectrum of this companion, and it's barely in the AGN region of the BPT diagram, but the error bars go into the composite region. So it's probably in AGN, but we need to do some more follow-up to know for sure. And this one, we don't have a spectrum of this one yet, but from photometric redshifts, we can tell it's at the same redshift. And you can also see hints of some tidal features and things. It looks like these are interacting. Now, I also have an undergraduate student, James Diekman, who's looking at the morphologies of the host galaxies of the double-peaked AGN in Sloan. Oh, yep. Yep.
Dual AGN, but you're saying in the central galaxy.
Yeah.
There's a dual.
Double-peaked.
Well,
so we don't know. Yeah.
But
right.
Let's just say.
Yeah.
a dual, there's supposedly two black holes in,
Right.
in the center one, and it also has a companion.
Right.
That may be an AGN. There's 3 black holes in this picture.
Maybe.
Right. You're
Yes.
being conservative, but you could say that's one thing that you're saying.
Yes. And we are doing follow-up observations of these guys. So, yeah. But these are ages spectra, so they're taken with hectospec at MMT, and the fiber is 1.5 arc seconds. So this is all just in the center of this here. We're not getting anything from these guys out here. Yeah. No. Good. Okay. So James is looking at the morphologies of the host galaxies of the double-peaked AGN in Sloan, and so he's asking the question: Is there anything different about double-peaked AGN compared to the general AGN population? So what he does is he takes the double-peaked AGN and he looks at a sample of other Sloan AGN that are matched by their host galaxy stellar mass and color. So you're trying to compare apples to apples here. Yeah.
So you're also matching them in AGN luminosity?
No. But I think he's writing up his paper now. There's a section about trends with AGN luminosity here.
I think the big conclusion from the TriStar plot that you showed and a lot of other work is that a lot of these host galaxy properties are strongly tied to AGN luminosity. So if you see any difference, it could just be that the double-peaked AGN are more or less luminous than the comparisons are.
I should have him match on luminosity as well and see if anything different comes out. That's a good point. Okay. So we're using several different tracers for host galaxy morphology because, as you know, it's a difficult thing to measure. So what he's finding, first of all, is that the double-peaked AGN have slightly higher Sursic indices than their comparison AGN populations. In terms of concentration, they're about the same, not much difference there. And then in terms of visual classification of the morphology, he used a couple of different techniques. One is Galaxy Zoo, which uses citizen scientists to assign visual morphologies to the galaxies. And there he's found that the double-peaked AGN have about 70% of them are in elliptical galaxies, whereas only 60% of the general AGN population are. This is all on average. And then he also looked at a Bayesian automated classification technique that uses machine learning to assign morphologies. And there he finds that 55% of the double-peaked AGN are in elliptical or S0s, and 50% of the other AGN are. Yeah.
The Sursic index and the concentrations, did you remove the AGN point source before measuring those?
No, we just took concentrations and Sursic indices that were measured in value-added catalogs. So,
the AGN point source will make it look bulgier than it really is.
Right. So that's why we did sort of as many different things as we could just to get.
The citizen scientists, for sure, I don't know about the Curtis Campani, but for the citizen scientists, this is also an issue because bulge looks like point source.
Okay, so I have a question for you. I think it's a hidden slide, though. Yes. Okay, so this is a question about Galaxy Zoo. So we took the 3 of the double-peaked AGN in Sloan that have already been confirmed as dual AGN, and this is them. And so we wanted to look at what their morphology classifications were. This one, I think 70% of Galaxy Zoo people said this was don't know. This is pretty clear merger to you and me. But I need to know more about how you taught them to identify what's a merger and why this wasn't a merger.
So in Galaxy Zoo 1, the merger button did not work as we intended because when things that were really unusual like this cropped up, a lot of people did not click merger, they clicked don't know. And this is basically because of the way we built the interface and explained to them what merger is. There's a great slide, for example, in Galaxy Zoo where Kyle Willard, who's doing the data reduction, run into the problem of we had a logo for disturbed galaxy as opposed to merger, and it was basically an elliptical ball thing that was sort of cut into 2 and sort of shifted, so like 2 halves that didn't quite fit together. And if you look at highly ranked objects in that class, you find every single galaxy in Sloan that has a bad pixel trail through it. So you have to be very careful how you phrase your question.
Okay.
So if you're using the Zoo 1 classification, So using the Zoo1 merger classification is very tricky. There's a lot of discussion of that in the Dargedal catalog, and the short of it is actually a fairly low threshold in the merger vote means it's clearly a major merger, because most people, when they looked at that, actually click don't know.
Okay,
So you have to go back to the merger fractions and pick your threshold, or just use the one that Darg.
Yeah, that's what we ended up going back and doing, because when we looked at all the don't know galaxies, a lot of them had sort of double cores and looked like cleared mergers. But okay, good. All right. Well, I've been talking about how to go through all these spectroscopic surveys and pick out the dual AGN. But sometimes when you're hunting for one thing, you find other things, other creatures that are not what you're looking for, but interesting in their own right. So I wanted to take a minute and talk about some of these other creatures here with the rest of the time I have. Okay, so this is a great one. This is Sloan 1356 plus 1026. This galaxy was originally studied and found to have an outflow by Jenny Green and Nadia Zatomska. This is one of the double-peaked AGN in Sloan. And this is a 4-color composite image of HST, BI, and H-band and Chandra data. And so the main galaxy is sort of here. It's got some tidal stuff down here. It's clearly a merger. It's got these 2 central cores that both correspond to AGN, we think. And then it's got this extended emission in H alpha that you can see here, that is this large galactic scale outflow. This is the long-slit spectrum from Magellan of the same object with the slit aligned like this. So we see the 2 cores as these 2 emission components in oxygen 3. We've got this bubble down here, and then these clumps here in extended emission. So this is an example of very large scale, 30 or 50 kiloparsec scale galactic outflow, and with 2 AGN in the middle of this merger. So the question is, what is driving this outflow? Well, it's not jet-driven, because this galaxy is radio quiet. It doesn't have any extended radio emission. It could be star formation driven, but in order to get that to work, you really have to push the energetics, because this outflow is 10 to the 44 to the 10 to the 45 ergs per second. So in order for star formation to drive an outflow that energetic, you'd need at least 100 to 1,000 solar masses a year of star formation. And that's just not consistent with the stellar populations of this galaxy, which show no young or intermediate age stellar population. These are only...
The energy of the outflow? How do you estimate the energy of the outflow?
Oh yeah, Jenny did that. And I think her 2012 paper. So she had this long slit spectra, and I don't think she had the X-ray data at this point. So I think it was purely from sort of the spatial and velocity distribution of the emission.
The velocity, you also have to know how much mass is sitting there.
Yeah. So she built a model of the orientation of the outflow that would be powering this and where it was centered and all that. And oh, I should mention the velocity extent here is about 500 kilometers a second. Oh, there's another galaxy up here that's blue shifted by about 200 kilometers a second. It's outside of this picture here. But there's another one here, so it's at the same redshift, it's close by. So it seems to be a part of this whole system too. So it's not jet-driven outflow. It could be star formation, but it's hard to get that to match with all the observations. So the likeliest explanation is that this is a quasar-driven outflow. So what this could be is an example of a galaxy merger not only with 2 AGN, but also powering an example of this large-scale quasar feedback that people invoke to shut down star formation, quench AGN, enrich the IGM. So this is a very interesting lobster that came out of our search.
The energetics of that process?
Yeah, the quasar process works out the best. I should mention that Jenny's also got ALMA data for this. So this ALMA data, so this will be covered in everything. Another interesting find was this galaxy. This is Cosmos J1000 plus 0206. So this is a step removed. This is not a double-peaked AGN. This is a galaxy that we found randomly through another process entirely, which was basically flipping through images of HST images of Cosmos galaxies. And this thing jumped out because it's got a very unusual morphology. So it's got this tidal tail that shows it's going through a merger. It's also got these two bright nuclei in the center that are separated by half an arc second, or about 2.5 kiloparsecs. And because this is a Cosmos galaxy, we also have all this multi-wavelength data that comes along with it. So all the multi-wavelength data shows that this is an active galaxy, but none of it has the spatial resolution to show whether the AGN activity is coming from one or both of these cores. So this could be 2AGN. We need follow-up observations. So we looked at this galaxy with Deimos on Keck, lined up the slit like this, and we saw these two emission components corresponding to the two nuclei. And Francesca Chavano and her group have also been working on this galaxy. They also independently discovered it, thought it was interesting, and did a lot of follow-up observations of it. And they found evidence for a broad line component that was offset from the narrow lines by 1,000 kilometers a second. So they suggested that this could be an example of a recoiling supermassive black hole. So in that scenario, this would be the recoiling broad line region. This would be the left behind narrow line region. But this could also be an example of dual AGN, where you see a type 1 AGN here and a type 2 AGN here. And the reason for the velocity offset is this was a triple black hole interaction. So two of the black holes merged to form this one, and then this one kind of got kicked by 1,000 kilometers a second this direction. So Laura Blecka did some simulations of galaxy mergers that could produce this system just to see if the morphology could give us any hint of what phase in the merger we are. Is this pre-merging of the black holes or post-merging? And she found that this sort of morphology with the tidal tail could be produced for both scenarios. So the jury is still out on what this object actually is, but whatever it is, it's interesting.
The spectra that you're showing on the lower right,
Mm-hmm.
object are they? Do they correspond to which of the two nuclei?
The lower right, these?
Well, any of them. I mean, are those spectra? But did this slit include both nuclei when the spectra were taken, or
Yes. I think they included both. But I have to look at the details of their paper again to be sure. But you can see the broad line there, each beta there. So I want to leave lots of time for discussion. So I'll summarize there. So I've presented a systematic technique for finding dual AGN using large spectroscopic surveys of galaxies. And as we get results from the X-ray and radio observations that tell us for sure which ones are dual AGN, we can refine the first two steps in the process to become more efficient at finding them. And the purpose of this systematic search is so we can build a large catalog out to higher redshifts of dual AGN so we can use them for studies of galaxy evolution. So dual AGN are actively accreting black holes in mergers, and they're also the smallest separation black hole pairs we've been able to observationally confirm so far. So they're exceptionally useful for studies of merger-triggered AGN activity, black hole growth, and the black hole merger rate. Thanks.
So you showed us this double-peaked emitter seems to be 1% of the AGN, total AGN population. But what about cases when two galaxies are merging and only one AGN is loose? Or what about if they're both quiescent? So is there a chance to figure out what is the relative abundance of one group versus the other?
Yes, yes. So when only one of the black holes is an AGN, you can look for a velocity shift of those single lines relative to the stellar absorption features. And that's something I've been working on that didn't find its way into this talk, but I can show you some slides about it afterwards if you want. And then in terms of if they're both quiescent, we're kind of out of luck in terms of observing them. But you can take something like the merger rate, the galaxy merger rate. How many dual AGN are we finding? How many single AGN are we finding? And try to tie it all together. Yeah.
They're pure double peak. How numerous are those that are single peak?
More numerous, much more numerous. Let me see. 5 or 10 times more.
Observed a mass-limited sample of mergers, where one of the nuclei I had was a spectroscopic AGN, and just asked the question if we look with Chandra, how frequently do we find the second one? And it was 1 out of 12. Small number statistics, but 1 to 2. In that
Pretend that a reasonable number of your double-peaked objects are really dual AGN, and you try to weigh the black holes and weigh the stars. Is there anything you can say that they fall systematically one side, the other, the M sigma relation?
Yeah,
or
that's
too light and they're about to grow.
That's
they're heavy and they're going to shut off their growth.
That's exactly what I have in mind that I want to do is measure these black hole masses, put them on M sigma, see how far off M sigma they are, to see how much mass growth they have left to do to get back on it. So that
from that, yeah.
No.
Yeah.
Yeah.
How are you going to
you
do
would
it?
need the cogenic or sigma.
Yeah, and that's part of the reason for the scatter and M sigma, right? Is for issues like that. So you can only measure what you can measure. But I'm hoping that it'll be useful enough if they all fall in one certain direction, and you can sort of average it and make some general statement about how much black hole mass growth has occurred at that point and how much more there is left to go. Yeah.
So there are about, let's say, 10 times approximately more single-peaked duals. That brings you up to, let's say, approximately 10% of all AGN, or 10% of all galaxies with at least one AGN are in mergers. So that brings you a little bit closer to the result that Mike Koss has found with his sample of that AGN. And they found, I believe, that about 25 to 30% of their BAT AGN are in mergers, either with another AGN or I believe with a galaxy. They
Right.
didn't look only at AGN, they looked
Right, and they looked at larger scales as well. So I'm just within these 3 arcsecond fibers, so I'm within about 10 kiloparsecs. Most of the AGN pairs that he found were at larger separations. There were 4 of them with separations less than 10 kiloparsecs.
But it is bringing the two numbers.
Right, it's bringing it together, right? So
Honestly, it was quite a big difference between these two results, even taking into account their separation. So now it seems that they're closer.
Oh, go ahead.
Can I ask you, in the short term, do we expect any other method to detect this kind of, other than double-peaked narrow-line?
Oh yeah, so Mike Koss's method has been successful at it. He's kind of, I end with X-rays, he starts with X-rays.
But X-ray, we do not expect a big instrument in the near future, right?
Oh, basically, anything that gives you a lot of data is good for finding unusual objects. So for right now, it's Sloan. LSST could be good, but the time domain is not as helpful because you're not going to see movement of these things on any kind of reasonable time scales. With something like JWST, you can start to push it down to smaller and smaller separations, down maybe even to the binary phase, or you can do the binary phase with really good radio observations with the best spatial resolutions you can do. So that's sort of where this all is pushing. So my perspective on it is we're learning on the phase where we can actually have a hope of spatially resolving things. So then we're ready in the future for new telescopes to apply it down to smaller and smaller separations, down to even hopefully the binary phase.
Once you find them, then you go after them.
Right. Right, yeah. Yes, because you just need a lot of data on a lot of galaxies. Yeah.
In your lobster,
Yeah.
there was not a lot of evidence of star formation, certainly not at the 100 to 1,000 solar masses per year. Have you looked for star formation in any of these others? Can you say something about whether they seem to be exhibiting star formation like you might expect from a gas-rich merger, or whether it's turned off because we're
Yeah. So another thing is that there have been these theory simulation papers, Phil Hopkins papers, that show that there's a lag between star formation initiated by mergers and AGN activity. So you may not necessarily expect there to be huge bursts of star formation at the same time you're seeing the AGN activity. Another point to make is that a lot of these AGN pairs should be happening in Eulers. So in the very beginning when I showed the ones that people found by chance, a lot of those were Eulers. And those were probably not finding with the Sloan selection technique because we're looking for double-peak narrow lines. So I'm sure these things are in Eulers. They're going to be messier to find.
Broadlines.
Yes. There are some double-peaked broadline ones as well.
Double-peaked 03, but they do have broad.
Double-peaked 03 and double-peaked broadlines, yeah. So the Sloan sample,
Broadline?
no, so the Sloan sample is mostly type 2 AGN, but there are some type 1 as well. Yeah, that's.
What fraction do you know?
It's small. So there's 340, so maybe 10%. And so we've been looking for any differences between the type 1 and type 2, and we haven't seen anything in the morphologies yet. And we just don't have enough confirmed dual AGN yet to look at the ones with type 1 and type 2.
So when you started selecting them, if you went by just the profile of the O3 line, that would not prevent you from finding dual starbursts.
Oh, we did the emission line diagnostics on both peaks. So both peaks are in the AGN region of the BPT diagram.
But
There's
did
this.
you find dual starbursts that you expect?
Yeah, so there's this Guy et al. Paper that shows you double-peaked AGN, one star formation, double-peaked star formation, puts them all out there. We're only looking at the double peak where both peaks are AGN.
Then a question that Todd Barson would ask, or maybe has asked, combination of starburst and AGN.
Yeah.
He claims that those are rare or non-existent. If you find two interacting objects that are both active, they're either both starbursts or both AGN. So, do you have anything to contribute to that?
There are some where one of the peaks is AGN and one of the peaks is starburst. We just haven't looked at any of those. We're just, since this is the first pass through, we're trying to maximize the number of dual AGNs, so we only look at the ones with both. But those other ones are out there published in the Guy et al. Paper, and people should go look at them.
Yes, that's right. And that might not be unreasonable because the interaction is neutral. Or maybe not. I mean, what are the relative, judging from the photometric properties, are they similar mass galaxies, or do you have very asymmetric kind of mergers with very extreme mass ratios?
Oh, in the cases where there are two stellar nuclei?
Yeah.
Okay, so thinking of the like Haifu's work, they seem to be within the sort of not anything smaller than 10 to 1. They're usually closer in luminosity than that. So they look more like major mergers on average.
Go ahead.
Okay, in your picture about the feedback in that image, I just wonder. So if you use the outflow to explain this double peak, so how about direction? Is it consistent with the direction of the?
Yeah, with the direction of the outflow. So you're just seeing sort of Jenny has a good diagram of this in her paper. There's some of the outflow is coming towards you, some is going away. And so that's consistent with this side producing the blue peak, this side producing the red.